When covalent bonding takes place, there's actually a complicated interaction between a whole bunch of different particles, even in a simple particle like hydrogen. Let's imagine we have two hydrogen atoms. So here they are far apart from one another. I'm going to draw a very simple sketch of that. Hydrogen, and there's the electron for hydrogen, and here's the atom. Here's another hydrogen atom, proton in the middle, that's the nucleus, and it has an electron. So there's the atom. Here are the attractive forces that are present. I'll draw these in red. This proton is attracted to this electron. It's also attracted to its own electron. This proton is attracted to this electron and to its own electron. So those red lines all represent attractive forces in this two-atom system. There are also some repulsive forces at play here. I'll draw these as green lines. This nucleus is repulsive to this nucleus. This electron is repulsive to this electron. Overall, we have more attractive forces going on here than we have repulsive forces. So these things are attracted to one another. Looking at this graph down here, what we're seeing is as you move closer and closer together, this is internuclear distance it's called on the x-axis, we're getting closer and closer and closer and closer to each other. And we see that the total amount of energy stored in the system drops. That's because the attractive forces are being relieved. It's like moving magnets together or letting a spring relax. So potential energy is coming out and kinetic energy is being released. And we see this curve showing that graphically. We get down to a certain spot where the hydrogens are fairly close to one another, and then the trend starts to reverse. The hydrogens, when they're 0.074 nanometers apart from each other, that's optimum. If you try to push them closer together, then the repulsive forces between the two nuclei and the two electrons start to take over, and then the energy begins to go back up. So the optimum place for two hydrogen atoms to be is right there when they're 0.074 nanometers apart. When they're that close together, well, we say that they're bonded. So another way of looking at this, besides just stability through full octets, is to look at the actual energetics of a bond. Energy is released when bonds form when they get to that optimum distance from each other, which for hydrogen happens to be 0.074 nanometers. So let's expand on that idea. When bonds form, potential energy that was stored in their attractions is released as kinetic energy. So that means when bonds break, kinetic energy is used to pull the particles apart and store energy in their positions, or positional or potential energy. Bond energy is the energy that's needed to break up 1 mole of a certain kind of bond when it's in the gaseous state. And this is usually given in kilojoules per mole. You have a reference table like this, I'm sure, in your textbook, and it's available widely on the internet as well. This would also be the same amount of energy that's released when 1 mole of a bond forms. When a chemical reaction takes place, many bonds break and many bonds form during the chemical reaction. The overall effect is the delta H of the reaction. That's why some reactions are exothermic and some are endothermic, because if they're exothermic, what's going on is it takes less energy to break up the bonds in the reactant species than is released when the bonds form in the product species. If they're endothermic, it's just the opposite. You have to put more in to break up the reactants than you get out when the products form. Let's look at an example. I'm going to give you a chance to try and figure this out on your own. Figure out, draw Lewis structures probably, and figure out what kinds of bonds and how many of them have to break in order for this reaction to take place. And then figure out how much energy goes in to break up those bonds using the bond energy chart. And then figure out how much energy comes out when the product bonds are formed using the bond energy chart. Look at the difference and determine if it's exothermic or not. You know that it's a combustion, so it should be exothermic. See if the bond energies tell the same story. Stop the video and give this a try, and I'll give you an answer in a bit. I'm going to draw this out in Lewis structures. So here's CH4, and I'm going to probably leave off the lone pairs just to make it quicker. Oxygen is a double bonded species, so that's our reactant species. And then CO2, carbon dioxide, is C double bonded to 2 O's, and water oxygen is single bonded, as it would have to be, to two H's, and we have two of those molecules. So there's our products. Now, how much energy goes in? Let's look at the reactants and find out how much energy it has to go in to break them up. Looking at our bond energy chart, we can quantify this. Here's what has to break. 4 CH bonds have to break. So here's our energy in, reactant side, breaking bonds. 4 times 413 kilojoules for every mole that this happens to. So this is CH bond, 413 right there. We also have to break up 2 OO double bonds. An OO double bond is 495. So 2 times 495 kilojoules. If I sum this all up, here's what I'd get. 1652 kilojoules for the CH bonds and 990 kilojoules for the double O bonds. When I add that up, the total amount of energy that goes in to break up these bonds in the reactant species is 2642 kilojoules. Now let's look at the output side. These are bonds that form, and energy will be released during these formations. So what bonds form? Well, a CO double bond and a CO double bond form. How much energy is that? Well, we're going to have 2 times whatever that CO double bond energy is. A C double bond O is 1,072 unless it happens to be in CO2. There's a little footnote on this chart down there. And it's 799. So 2 times 799 kilojoules. That energy will be released as the C double bond O's form in carbon dioxide. And then I'm going to form 4 OH bonds. If I look at OH on the chart, it's right here. That's a 467 kilojoule bond. So 4 times 467 kilojoules. Multiply these out. 1,598 kilojoules for the CO bonds and 1,868 kilojoules for the OH bonds. When I add the two together to get the total energy that's released, I have 3,466 kilojoules. So overall, I will have 3,466 come out of the system, and I will have to put in 2,642 kilojoules. The net is 824 kilojoules will be released per mole that burns. So we could say that delta H for the combustion of methane is going to be negative 824 kilojoules per mole of methane. Okay, give this one a try. This is a reaction that you might recognize. CO2 is reacting with water here to produce C6H12O6 and 6 O2s. I'm going to have to give you a clue as to the structure of this so you know exactly what bonds break. You're going to have to know exactly what bonds form in the C6H12O6. So I'm going to go to my problem-solving tablet, and I'll draw that sketch for you so you can solve this problem. It's going to be 6 carbons in a row. The last carbon's got a double bond to an O, single bond to an H. And then we alternate H and OH up and down for most of this chain. And then this terminal carbon has got 2 H's and then 1 more OH. So that's the structure that you're working with. And then you'll have another product and you'll have 2 reactants. So do your best, and I'll give you an answer in a little bit. Well, here are our 2 reactant species. You've got a carbon dioxide, C double bond O, on 2 sides. And we actually have 6 of them. Those bonds are going to have to be broken up. And then we have water, which is a O single bonded to an H 2 places. And we have 6 of those as well. Those are producing that C6H12O6. And we have 6 oxygens. And we know oxygen is double bonded. Okay, let's look at the energy in. The bonds we have to break are 2 double bond COs, 6 times. So in all, 12 times the double bond energy of a CO bond. And in carbon dioxide, remember, that's 799. So 799 kilojoules times 12, that works out to 9588 kilojoules. We're also going to have to break up OH bonds, 12 of them, 2 per molecule, 6 molecules. So 12 times 467 kilojoules, because that's what we have for an OH bond. That gives us 5,604 kilojoules. So when we sum up the energy needed to break up all the bonds on the left-hand side, we get 15,192 kilojoules. Now, what's going on the right-hand side? Let's look at the O2s first, because they're going to be easiest. We're going to form 6 OO bonds. So this is the output energy now. 6 times OO energy, which is 495 kilojoules. And that comes out to 2970 kilojoules. We're also going to form a bunch of OH bonds. How many? 1, 2, 3, 4, 5 OH bonds will be formed. So we'll release 5 times whatever OH's bond energy is. Oh, that's 467. We already looked that up. This sums up to 2335 kilojoules. We're also going to break up some CO bonds. How many? 1, 2, 3, 4, 5. And that's a C double bond O, so we're not going to count that one. 5 times 358 kilojoules is what you get when you look that up. A CO single bond is 358 kilojoules. So when we sum that all up, we end up with 1,790 kilojoules. There are also going to be some CH bonds that we're going to form. 1, 2, 3, 4, 5, 6, 7 of them. So 7 times a CH bond is 413 kilojoules. That's going to give me a total of 2891 kilojoules. What's left? Well, we have that C double bond O, and we have some CC bonds as well. So we're going to form 1, 2, 3, 4, 5 carbon-carbon single bonds. A carbon-carbon single bond is 347 kilojoules. When we form 5 of them, we will release a total of 1,735 kilojoules. And then the one last bond we're going to form is a CO double bond. So 1 times 745 kilojoules, because that's what a CO double bond is if it's not in carbon dioxide. Add this all up, you get 12,466 kilojoules released. So, all told, this is the story of this reaction. I'm putting in 15,192 kilojoules. I'm releasing or putting out of the system 12,466 kilojoules. Net result, 2,726 kilojoules. It's a positive number. More goes in than comes out. Here's what that means. Delta H for this reaction is positive 2726 kilojoules. If you recognize this reaction as the photosynthesis reaction, you probably knew that it's endothermic. Energy has to go in from the form of sunlight for photosynthesis to take place.